And greetings. Welcome to the Evidence Reasons Academy. The last round, things weren't going so well on technical issues. I had a disconnected USB cable, and so I didn't have audio. In the background is World Series, inning 9, game 4. Astros are ahead 5-0, trying to tie up the series to 2-2. Right now they're behind 2-1. And so far it's a no-hitter in the 9th inning. This could be historic. So that's what's going on in the background. There has been, people know my feelings about the Big Bang cosmology, that I think it's wrong. It's not just because I'm a young Earth creationist. I actually became a young Earth creationist because even 20 years ago there were rumors the Big Bang was in trouble. The quiet whispers among grad students of physics, the discontent among respected physicists, and just kind of that undercurrent in my undergrad university. 3 respected professors openly came out and said the Big Bang never happened. It is a cultural phenomenon that's just driven by momentum. People want to claim that they figured things out, and it is really bad when they have to say, hey, we have no clue how things really happen, and things don't square up with the data. They want to just try to patch it with a promissory note. But when a theory like the Big Bang keeps, as new discoveries are encountered, when a theory like that comes forward, and as new data comes forward, they keep physicists saying, well, we have to revise our understanding of physics. It's like, no, the problem is maybe the Big Bang is wrong. We don't have to maybe substantially revise our understanding of physics. Maybe we just have to dispense with the Big Bang, and the physics is a little bit simpler, not so complicated. And when we're invoking imaginary things like the inflation field, dark matter, dark energy, we can't really test directly in laboratory conditions. That is kind of disconcerting. So, let's just open the possibility, but it could be that the paradigm is just totally wrong. And with the James Webb Telescope, it's just looking even worse. To that end, there are things in my study of cosmology that I didn't went in one ear, out the other, and sometimes things are being thrown so fast at you. It may have been covered, the phenomenon that I'm going to talk about. I want to extend a salute, hat tip to mrJety89, who sent me an email that linked to this phenomenon that it's not really a phenomenon, it's a prediction of the Big Bang theory. In normal Euclidean, nice Euclidean geometric space, if I hold an object, as that object moves farther away, it looks smaller. And the farther and farther away I go, it's going to continue to look smaller and smaller and smaller and smaller. That's a nice Euclidean, Euclidean type universe, non-expanding type universe. Similarly, if we have objects that are of similar, assumed, hypothetically, let's say we have objects of similar size, and let me get a book that's about the size of this one. These are both books that, clearly this one's smaller than the other, the red book. They're both electromagnetic theory books. I'm actually starting to like the Griffiths book better than the one by Haidt. The Haidt one's well worn, and I kind of regret having been assigned it. But I'm holding them side by side. They look about the same size. So if one is farther away and one is closer, you could see that they have different. It looks like they look smaller, what we call the angular size. It's not that it's physically smaller, but the angular size in terms of the amount of the amount of pixel space it occupies is smaller. So I could flip this and you could see. So in nice Euclidean geometric space, that would hold true if it's not expanding. So the thing is, in Big Bang cosmology, that doesn't hold. If space is expanding, and let me show, if we hypothesize that space is expanding and it has we assume some other properties, then instead of the continuing decreasing size with distance, and redshift is a proxy for distance, the formula is kind of intricate how to make this work. But if we assume that redshift as a proxy of distance, the farther, the higher the redshift, and I'm assuming some knowledge there of what people mean by what it's meant by redshift. But at some point, the size of the galaxy, if we have like hypothetically the same class of galaxy with the assumed approximate same size, then the farther out you look, it doesn't really shrink like you do in Euclidean space, which is a very interesting prediction. And this prediction looks like it is at serious risk of being falsified, because if we start, and it's a little more, it's subtle here. There are so many rescue devices and epicycles, quote unquote, in Big Bang cosmology. They can kind of slip out of anything by invoking some new law of physics or a promissory note for some future understanding. And if you'll indulge me, I am really curious if the no-hitter has been maintained. No, it looks like they had a walk, and there's one out, one walk, and a ball. So maybe the no-hitter's not going to, we'll see. I mean, Philadelphia is fighting for their life here, trying to win this game. Anyway, where was I? They're invoking all these rescue devices, and at some point maybe one has to think maybe it's just fundamentally wrong that when one needs to keep invoking more and more rescue devices because you're surprised by something, that probably means, that just doesn't look good. It doesn't instill confidence that the theory is fundamentally correct. Maybe, and this leads to kind of a funny complication. The young Earth creationists, a few of them, not all, because some young Earth creationists believe in the Big Bang, some don't. They have to account for distant starlight with different mechanisms, but they may think the Big Bang's fundamentally correct. There's the majority, I would say, would prefer that the Big Bang's wrong. But then we have the eternal universe advocates that say matter and energy have been here forever. And so there's kind of strange bedfellows with people wanting to see the Big Bang kind of being taken down. You have the hardened atheists and also the young Earth creationists kind of briefly on the same side of the issue regarding the Big Bang. So this is all kind of funny here. And looks like we had the second out. The no-hitter is still going, and there's one more out to go. So we'll see if this is a historic World Series game. Anyway, so what's the issue here? Going back to the central issue is we don't get this nice thing like I did with the books, where the farther and farther you go out, it looks smaller. It just, at some point, it's actually going to start to look bigger. And the math for that is a little bit, I provided a link in the video description that talks about how to do this calculation. I had actually gotten through some of this in my cosmology class with the Friedman-Robertson-Walker metric, and then you work through the math. And it's not very pleasant. Actually, this isn't too bad. It's just uncomfortable. right? I mean, one can get through it in an hour or so, in a few hours or so. And so I vaguely recall the professor walking me through how all of this will work with all these parameters. And this was my 9th of 10 classes, and I was just eager to get through it. I wasn't, I didn't take it as seriously as I should have. I didn't get as much out of it. I remember I was working on a side business at the time. So this explains, for those who want to see how this particular, how this calculation was done, it is done with the math laid out in the link I provided. So this is basically not an empirical claim. It is a theoretical claim that is subject to falsification. So what happens if we find that this isn't true? Well, we would say the Big Bang is probably false, or that maybe the galaxies are a lot smaller when they're really at the beginning of the universe. Smaller and brighter, and then they get bigger and not quite as the luminosity is not as the brightness per surface area is not as bright. There is a term, and I have to. This is where I get really messed up. There's brightness and luminosity, and I am totally embarrassed. I need to know what these terms are. Okay, so I provided the lecture that gives you all that for the angular size. So what's the difference? Luminosity. Let me just look this up. And unfortunately, I hope this is uniformly true throughout all of the luminosity.org. Luminosity. That's not what I wanted. Luminosity definition. And let's see what happened. See if we got a no-hitter. It's still a no-hitter. And it's final. Houston wins with a no-hitter 5-0. Oh my goodness. Sorry, this is the World Series, guys. This is serious. I was looking it up on the internet, and you could see kind of the celebrations there. They're interviewing the pitcher who had 6 no-hit innings, and then his relief pitcher had 2 no-hit innings, and then I think the closer, I'm presuming it was a different guy, the closer had 1 no-hit innings for a total of 9 no-hit innings. This is historic World Series. But the World Series isn't over. We're in game 4 of 7. So anyway, luminosity. So let's look at the Wikipedia definition. Luminosity is an absolute measure of radiated electromagnetic power light, the radiant power emitted by a light-emitting object over time. In astronomy, luminosity is the total amount of electromagnetic energy emitted per unit of time by a star, galaxy, or astronomical object. So the unit is in watts. Okay, luminosity is in watts. All right, I got that. So now let's look at the definition. Brightness. Now this is good. See, this is why I'm doing these shows, because I need to learn this. Okay, magnitude. In astronomy, magnitude is the unitless measure of the brightness of an object in a defined passband. Brightness is an attribute of visual perception in which the source appears to be radiating or reflecting light. In other words, brightness is the perception elicited by luminance of a visual target. See, luminance is a photometric measure of the luminous intensity per unit area of light traveling in a given direction. It describes the amount of light that passes through, is emitted from, or is reflected from a particular area and falls within a given solid angle. The perception is not linear to luminance and relies on the context of the viewing environment. Brightness is a subjective sensation. Oh, come on. Okay. The Federal Trade Commission has assigned an unconventional... Oh boy. This is going to be... I'm now not being very happy about this. Because you think they could give something in nice units and I'd figure it out. Okay, let's look at Britannica here. So let's look at stellar intensity. Make this bigger. Stellar brightness are usually expressed as by means of their magnitude, a usage inherited from classical times. A star of the first magnitude is about 2.5 times as bright as one of the second magnitude, which in turn is some 2.5 times as bright as one of the third magnitude, and so on. A star of the first magnitude is therefore 2.5 to the fifth, or 100 times as bright as one of the sixth magnitude. The magnitude of Sirius, which appears to an observer on the Earth as the brightest star in the sky, save the sun, is 1.4 Canopus. One is minus 1.4 Canopus. The second brightest has the magnitude of 0.7, while the faintest star normally seen without the aid of the telescope is of the sixth magnitude. Stars as faint as the 30th magnitude have been measured with modern telescopes, meaning these instruments can detect stars about 4 billion times fainter than the human eye alone. The actual measured brightness of stars give apparent magnitudes. These cannot be converted to intrinsic brightness until the distance of the object concerned are known. The absolute magnitude of a star is defined as the magnitude it would have if it were viewed at a standard distance of 10 parsecs, since the apparent visual magnitude of the sun is minus 26.75. Its absolute magnitude corresponds to the diminution in brightness by a factor of 2,062,650 squared, and is using logarithms, is a 4.82 magnitude. Oh boy. There's some basic astronomy here that I don't know. I didn't realize it was going to be this complicated. Now, okay. Magnitude and brightness. So let's go back to the Wikipedia article. So magnitude in astronomy, just going back from that, I didn't know this is going to be so nasty. Such that a 1 magnitude star is exactly 100 times brighter than a 6 magnitude star. Okay, we covered that. Astronomers use two definitions of magnitude, apparent magnitude and absolute magnitude. The apparent magnitude is the brightness of an object as it appears in the night sky from Earth. Apparent magnitude depends on an object's intrinsic luminosity, its distance, and the extinction reducing its brightness. The absolute magnitude describes the intrinsic luminosity emitted by an object and is defined to be equal to the apparent magnitude that the object would have if it were placed at a certain distance from Earth, 10 parsecs. for stars. Defined as the apparent magnitude. The apparent magnitude is the brightness of an object as it appears in the night sky. And I wish they'd define brightness. Brightness, this is why I'm so luminance is the perceptual. Luminance is the intensity per unit area of light. Luminance is the intensity per unit, describes the amount of light that passes through, is emitted from, or is reflected from a particular area. This is like so hard to understand. In astronomy, magnitude is the unitless measure of brightness of an object in a defined passband. Okay, so I'm going to have to study this before I try to make some pronouncements. So we have luminosity and brightness. Surface brightness. Okay, so there is something called surface brightness. Surface brightness. Surface brightness. In astronomy, surface brightness quantifies the apparent brightness or flux density per unit angular area of a spatially extended object such as a galaxy or nebula, or of the night sky background. An object's surface brightness depends on its surface luminosity density, its luminosity emitted per unit area. Okay, so surface brightness is not the same as brightness. Okay, so there's photometry. And let's see, the units are, okay, this is, oh boy, they have all these. Why can't they do surface unit brightness in terms of watts per square meter or something? Oh, goodness. I mean, it would be like helpful if they converted all those astronomy units into like watts per square meter. Then you know, poor little physics students could probably understand that. Watts per square meter. Okay, so this is painful. So luminosity is the number of watts of an object, and if the object's total wattage is compact into just a small angular size, if it's compacted into a small, not angular size, but into a small area that all the light is coming through, then we can say it has a higher surface brightener than something that's diffuse. And that's going to be significant. So as we were looking at this picture here that I was showing earlier, what should happen is that not only does, the funny thing is the size keeps increasing the higher your redshift for presumably the same class of galaxies, but its surface brightness should decrease dramatically. And this was a prediction of the Big Bang, and it failed it. I'm going to read the passage here by Michael Disney, who is a respected astronomer, and I put the link there. He says here, this is and he has a table here, it's beautiful, of where the Big Bang is not confirmed, all of the predictions that need to be confirmed, and it has too many free parameters. We don't have anything that is 0 or higher. When you have these negative numbers, that means the prediction of the Big Bang has not been unequivocally confirmed. So, let's look at the surface brightness test, the failure. It's the Tolman. Okay, Tolman calculated that the surface brightness, the apparent brightness per unit area of receding galaxies should fall off in a particularly dramatic way with redshift. So, what we should see here as we have a higher redshift, the size of the galaxy should be getting bigger, and they should be getting very, very much dimmer. Tolman calculated that the surface brightness, the apparent brightness per unit area of receding galaxies should fall off in a particularly dramatic way with redshift. So dramatically, in fact, that those of us building the first cameras for the Hubble Space Telescope in the 1980s, so he was presumably helping work with the Hubble Space Telescope, so dramatically, in fact, that those of us building the first cameras for the Hubble Space Telescope in the 1980s were told by cosmologists not to worry about distant galaxies because we simply wouldn't see them. Imagine our surprise, therefore, when every deep Hubble image turned out to have hundreds of apparently distant galaxies scattered all over it. Contemporary cosmologists mutter about, quote unquote, evolution. But the omens do not necessarily look good for the Tolman test at high redshift. If the expansion were to fail, then so would the entire superstructure of the Big Bang. Okay, this is really funny. We talk about biological evolution, so when you use the word evolution, we're, in cult, basically in our culture, we're usually talking about biological evolution. Well, there is evolution of stars and galaxies. We, just as a shorthand, we won't say galactic evolution or stellar evolution. We'll just use evolution if we're talking in the realm of cosmology. The context will tell you we're talking about evolution of, like, say, galaxies if we're talking about galaxies. And so how do we solve the problem of the Tolman surface brightness test? Evolution! Reminds me of Haeckel's quote, evolution is henceforth the magic word by which we will solve all riddles. Evolution is henceforth the magic word by which we will solve all riddles. Just to be careful here, people have asked me where's that quote from. You would have to translate there were two versions of the book, the natural history of creation, the German version and the English version. The English version does not have that phrase in it because Haeckel wrote a specific preface for the English version, and they never translated the preface in the German version for the English translation. So he was writing to two different crowds, and it's only in the original German Natürliche Schöpfungsgeschichte, that was the title, the natural creation story. In the preface there, the forward, the preface, the vorwort, it's in there. Evolution is henceforth the magic word by which we will solve all riddles. So, what do they do to explain why the galaxies are... They don't seem to be following this. What you see is the farther you look, they get smaller and smaller and brighter. The surface brightness is brighter and brighter, and these are smaller and smaller. And it got really bad with the James Webb Telescope. How bad did it get? I'm going to tell you. And I didn't understand it when Eric Lerner was not explaining it too clearly. And you know, he addresses astronomers. The astronomers totally, a lot of them know. So according to the Big Bang, we're going to see this, and the galaxies will get slightly bigger and bigger the farther out you look, but they're going to get so dim, according to cosmic evolutionary theory, they'll get so dim you won't see them. Michael Disney called them out on it because he and his colleagues were working on the Hubble Space Telescope cameras, and they said, don't worry about it, you're not going to see it. He said, imagine our surprise when we did see it. And so what do? Evolution to the rescue. They said, well, the galaxies were tiny and very, very bright. They're teeny tiny and very, very bright. And the problem is they got tinier and tinier and tinier and brighter. The surface brightness got brighter and brighter. And that's why when the first images came out, people were saying this. Yeah, I was up till 3 a.m. last night. I said, everything I've been thinking about my whole life has been wrong. I'm just like, yeah, I'm sorry about that, but that's probably right. You said it, not me. That you're the one that's up late at night thinking that everything you thought about is wrong. And it's like, well, it's not your stellar evolutionary model that's wrong. It's the Big Bang that's wrong. So now let me bring up what Eric Lerner brought up, and it's not necessarily the clearest diagram. And it's unfortunate he put his picture up here. He could have put it down here. It says, is the GHZ2 a Mighty Mouse galaxy? Okay, this is a galaxy that is at redshift 20. This is like toward the limit of how far you could see out there. Now, there is a distance formula calculator. I found it on Ned Wright's website. You can compute the redshift. You supply the redshift, it'll tell you how many light years away it is. Maybe I should do that. Let me see if I can find redshift to distance calculator. And okay, let's look at this, see if I could find it. There's a cosmology calculator. All right. Let's see if I can get this cosmology calculator to work. There's some parameters you have to assume. So, like, let's say okay, let's do 1Z. Okay. I'm going to just reset this, guys. Let's see. I think it wants open. I'm sorry, let me just try this again. I'm getting a little aggravated. This is not the best user interface. So it is now... Let me just change this. Okay. This is not the most user-friendly calculator, but let's try to do this. So the light travel time, 11.549 gigayears, billion years. Okay, 11.549. Okay, so at a redshift of 20, the distance would be, the light travel time is 13.54 gigayears, almost at the beginning of the universe. Oh my goodness. Okay. The age of the universe was 0.18 gigayears, 180 million years old. Only 180 million. So let's just say we had a redshift of 30. I'm just going to throw that number out. Okay, 100 million years old. So a redshift of 20 is 180 million years old. So looking at the universe at 180 million years old, I think it was a redshift of 20 or 15. Let's just put 15. I don't remember the specs that he gave. So, but this is still like 207. This is like 300 million years, 272 million years in the past. I mean, at the beginning of the universe. This is almost at the beginning, on a percentage basis. So this is how we convert redshift to distance. Really, the light travel time. Redshift, in terms of, it's just funny how it is. I don't know how we can actually phrase that. It's a lot farther now. The radial distance, it's at 34.187 gigalight years. So the distance is 34.187 gigalight years. The light travel time was 13.449 gigayears. The age, we're looking at the universe at the age of 272 million years ago. Okay, so now let's look at this mighty. Greetings, Seamus. Greetings, Seamus. Let me just say hi to Seamus here. One moment. I'll get rid of this. There was a no-hitter in the World Series. Congratulations to the Houston Astros. They lived to fight another day. And let me say hi. Greetings, Seamus. So, we don't actually know the radius of this galaxy. That's the problem. We don't, if we knew for a fact how big, what the diameter or radius of the galaxy was, we could settle this. There's unfortunately a lot of circular reasoning that you have to infer the radius based on your model and the brightness. This is what is so problematic when you're getting data. They'll claim one thing, but you can't use it to prove something else because it may be all circular reasoning. So we actually don't know how big this is. All we know is that it has a certain brightness and it has a certain angular size that it looks like in the sky. So to get around, yeah, great to see you too, Seamus. To get around this problem here, okay, so, I'm sorry. It's to get around the fact that we're seeing what looks like to be a very tiny a galaxy that doesn't look big. It looks very small, so they're just going to assume it's really, really small, and it's also really, really bright. So when they take the Big Bang parameters, they're going to take the Big Bang parameters and they're going to affix a size to it and say, well, we'll just assume that it evolved from that size. And this is where it starts to become very problematic for the current prevailing models. It's like you're having to assume that you had all this matter that just got clumped in together, and it's like teeny tiny galaxy, but it's so bright and dense, and somehow, if that starts to be common, they just get bigger and bigger over time. And this is why they're having headaches about this, guys. I mean, this is not looking good at all. But let's look at Eric Lerner's description here. He said, if we, based on what we know, if we use the Big Bang, this galaxy is 90 parsecs across, which is teeny tiny. It has a certain luminosity, which is the total output in watts, and they have their own they have their own measure of this. And I'm not familiar with the units. I wish they'd put the units. He needs to put the luminosity per the number of watts of the sun, and that turns out to, so this is like 10 to the 11th, on the order of 10 to the 11th suns. And the surface brightness is 580. The surface brightness observed is 580. And the volume brightness is 14,000. I mean, this is just, he was saying this is just insane. Whereas if we don't assume the Big Bang, this one is comparable in size to our Milky Way galaxy, has about the same luminosity. I mean, they all have comparable, same order of magnitude luminosity. But the surface brightness is that of, like, say, the Milky Way, and comparable to the Milky Way. Lerner had related that. So this really, they're like, how do you get a galaxy that's so tiny and bright like that? And that's giving them headaches. They said that shouldn't be there. Well, maybe the Big Bang's wrong, and maybe it's like a galaxy that's probably more normal. It just it's obeying the Euclidean geometry in terms of, like, when I was trying to show, the farther out you are, the smaller something looks. And it also maintains its surface brightness. I think surface brightness is invariant. In a Euclidean geometry, non-expanding, surface brightness is invariant with distance. Surface brightness, which is the brightness per square per area, per square meter, the brightness per square meter, it's going to be the same. Or per square angular size, something like that. Per square, so the number of pixels, I guess, on your in your visual field, the number of pixels it occupies, it's going to maintain that same ratio of the total wattage per pixel, something like that. I'm not getting this right. I need to talk to an astronomer to work me through this. But that's what I'm getting from this. And I think this is looking really bad for the Big Bang. So the question is, what is the cosmology? And I don't think anyone knows. It's really nice when you can tell a creation myth, a secular one in this case, about the Big Bang, and pretend you figured it out. It's very uncomfortable to say, hey, we have to go back to the drawing board. And it's really hard to say everything we've been telling the public for the last, say, 70 years, or however many years since the Big Bang idea came about. What's Penzias and Wilson? When was Penzias and Wilson? When were they awarded? Penzias Wilson. 1978 Nobel Prize, but they made the discovery 1964. So 1964, so that's about not quite 60 years ago. Not quite 60 years ago. So that's kind of like when they started claiming victory for the Big Bang. So they're going to have to say maybe everything that we've been teaching in the textbooks for like about the last 60 years is wrong. And we've invested millions and billions and billions of dollars to support a creation narrative of the cosmos that is inaccurate. That's a lot of momentum, so to speak, that has to be stopped. And I don't know, cultural ideas are very, cultural myths are very hard to undo. We still have the cultural myth of George Washington chopping down the cherry tree and all sorts of things that we've now known were fabrications, and we have the paper trail for where the fabrication came about. And we certainly have the paper trail for how the Big Bang theory came about. And, I don't know how long it's going to be before it just starts to break as a theory. I mean, a theory that can keep building epicycles and new claims of new physics, in some respects, that's just going to keep it going. Because then said, like, this is a new exciting field of research. How are we going to discover new theories of physics to solve the Big Bang? And if it's fundamentally wrong, the number of epicycles is just going to be infinite. This is a dream for researchers that are wanting more and more grants. Oh my goodness, this is scary. It's fundamentally wrong. Just like geocentrism was getting all these epicycle fixes, and it was fundamentally wrong. So, what can I say? It looks like the Big Bang cosmology. It's not, guys, you keep hearing, it's like we keep getting confirmation. It's true. It's like, no, you get a lot of counter evidence, and cosmology is in crisis. I saw this coming when I was studying cosmology. So there you have it. I stumbled through this. This is what the academic channel is for. It's partly for me to try to learn things and then try to communicate it. I invite commentary by qualified people to try to get all the terminology I may get wrong corrected. Snarky comments, those people are just tossed. I mean, if I feel that they're not going to contribute one iota to helping anyone understand anything, it's like I have to say goodbye. I just don't have time to deal with it. So this is not looking good for the Big Bang Theory. I quoted a respected astronomer, Michael Disney, saying that this was a surprise and that they were doing, he calls the fixes, he said this is ominous that they're having to make these fixes. He specifically, let me just read it again. Tolman calculated that the surface brightness, the apparent brightness per unit area of receding galaxies, should fall off in a particularly dramatic way with redshift. And what do we see in this Mighty Mouse galaxy? The surface brightness increased. The surface brightness increased. This is not good, guys. It went the opposite direction. So he says, the surface brightness, apparent brightness per unit area of receding galaxies should fall off in a particularly dramatic way with redshift. So dramatically, in fact, that those of us building the first cameras for the Hubble Space Telescope in the 1980s were told by cosmologists not to worry about distant galaxies because we simply wouldn't see them. Imagine our surprise, therefore, when every deep Hubble image turned out to have hundreds of apparently distant galaxies scattered all over it. Contemporary cosmologists mutter about evolution, but the omens do not necessarily look good for the Tolman test at high redshift. If expansion were to fail, so would the entire superstructure. It's failing, guys. It's failing. It's not looking good. The rescue, there are all sorts of rescue devices, and they just look so kludged. So I want to thank Mr. Jetty for helping me to be acquainted with this and to help revisit some of my studies of cosmology, which I obviously didn't learn very well, or as well as I had the opportunity to. So with that, glory and honor to our Lord and Savior Jesus Christ. During these nerd torture sessions are the cross we have to bear if we're going to be creationist researchers. Take care and God bless you, and let me see if I could find some music to close this out.